Okay, why did it move all the way back? Okay, that's fine. You guys are looking at the kitchen today. Anyway, good morning, everybody. And where today is, what is it, the 12th of November. So next week we will have class. Hopefully we'll get into the solar system. So we'll try to do things into the content so that we can catch up a little bit, because I think we are a day or two behind. And we should be fine, hopefully. And then we will have Thanksgiving break. After that, we will finish the last few chapters in the last week of instruction. Then we will have our last exam, and then the final. Okay, so this is where we are right now. There will be at least a few more quizzes after this exam, before the last exam. And that's basically, in a nutshell, what's going on. So there will be at least 2 quizzes, potentially 3, okay? So that's basically where we stand. So I know there are quite a few people today who are not here, and usually that happens after the holidays. Things like this always tend to happen after, since we had a holiday yesterday. Anyway, let me get into first of all, the content of today, which is the, which is plate tectonics and the Earth's interior, basically. And for that, what I did, actually, I boiled an egg. Actually, I boiled more than an egg. I bought 3 for a salad later on. I don't know if you can see it or not. This is more or less how the Earth would look like if you look at it. I mean, there is a thin crust layer in here, but I already peeled that off, so I cannot cut the egg with the shell on it. So that would be the crust. That's where basically most of the things that we see on the Earth. Then you have a mantle, and the mantle actually is the thickest part of the Earth. And then inside of that, there is the core. So the first question of the day is at least name the 3 main layers of the Earth, okay? So to go by Sarah's recommendation, I know she's not here today, but let's put the question in there. There are 3. I mean, the core itself is divided actually into 2 regions, the inner core and the outer core, because of the fact that one of them is liquid and the other one is, because of the pressure, is solid. The inner core is solid. So name the main layers of the Earth. Earth has to be capital, okay, when we're talking about the Earth. The Earth's structure, okay? What I mean by that is the inner one, okay, not the outer. No, I don't mean the atmosphere and the other parts, okay? So that's basically the ones. So they are crust, mantle, then the core. Technically, the core is actually 2 layers, inner and outer, okay? So this is the first question of the day. For those who are watching the recording, hopefully you guys got this thing in here. For those who are going to come later, I'll try to repeat this question, because some of the people who come later in the class, maybe come a few minutes late, they will miss on these first questions. And then what happened after that is they think that they covered everything, but they will miss on the first few questions that happened before they join us, assuming that they are not going to go and watch the recording if they thought that they attended the class. So this is the first question of the day. So we're going to talk basically of what led us to believe, what led us to know the fact that the Earth has this structure, okay? And the key thing in here is the seismic waves, earthquakes, basically, okay? We cannot dig. There is no way you can dig all the way to the core, to the center of the Earth. This is it's impossible to do because of the fact that tremendous pressure and heat that is involved. And even if you dig basically several, basically dozens of miles, if you can, it's going to collapse on itself because of the sheer pressure. Especially we'll see that the mantle itself has a portion that is molten, and that will result in motion in it. So you cannot dig through an ocean, for example. Can you dig a hole in the pond? I mean, on the surface itself, not on the water itself. No, because it's going to collapse on itself. So that's the reason why you cannot. So what we're left with the seismic waves, basically earthquakes on Earth, which is a really tremendous tool, because it helps us know exactly how the Earth structure is structured underneath. And also, it took us to another aspect of astronomy. Actually, today we have what detects quakes on Mars. They're called, of course, not earthquakes on Mars. They're called Marshquakes. Okay, so Martian quakes. So they are different than those of the Earth. To learn more about its internal structure. So that's basically what we what we're trying to do also, which led us to which gave us actually an idea of how all of the planets basically have some sort of a structure underneath, of course, with some variations that we will get to them when we get into the solar system. So Earth's internal layers, and I already mentioned the three main ones. Actually, there are four of them. If you really be accurate, the four are due to the fact that initially we thought that the core itself is only one layer. It turns out to be two distinct layers, okay, in terms of density and in terms of phase also. One of them is solid and one of them is liquid, okay. And then we're going to talk about the continental drift, which started as an idea and then later on supported by a lot of what looks like evidence. But there was a major criticism to the idea that Mr. Wagner came up with in the early 1900s. And that was what causes these continental drifts, okay? Of course, it was dismissed as until later on there was evidence for it, more into the force what causes it, and namely the heat in the mantle that causes this convection motion in the mantle itself, basically. So this is hot. Let me see. Hopefully it doesn't fall. Okay. So the white in here of the egg is hot actually, and it's like boiling, like you have your boiler when you boil the water. So it's moving, and it does is the crust, which is a thin layer that sits on top of it, which is really made up of different plates. It's not just one big layer like the skin of the shell of an egg. So it's actually made up of a different plates, and those plates, because of the heat, they are basically driven into motion by this convection. So this is basically how we know now actually what causes this continental drift, or at least the force behind it. And then the idea was moved from being just basically a hypothesis to an actual theory supported by evidence and observation. Okay. Then we're going to talk about the plate tectonics, which is really the result of this whole continental drift. And of evidence, of course, through earthquakes and through basically faults in the Earth itself, to the fact that there is actually motion of these plates, okay? And there is actually, if you look at at any map of the Earth, for example, the biggest suspect that makes you really suspicious, if you look at the two continents of Africa and South America, you can actually fit them perfectly, okay? They fit perfectly into one another. That's really how Mr. Wagner actually started with the idea. When he looked at that, he said, maybe there is, and actually he did. He went in and looked into more evidence, for example, onto the different rocks from one continent and the other continent, and there is similarity in structure. He looked at also actually and the plants themselves and the fossils actually from hundreds of millions of years before, and they indicate that these two continents were actually joined, were part of one. They were actually one thing. He called it Pangea at that time. So that's basically how the whole continents, not just Africa and South America, all of them, they were only one big continent called Pangea. And because of the continental drift, they started to drift, and they continue to move. Actually, this is not something that stopped. It's continuous, but it's super slow. In other words, it takes millions of years for this convection. Unlike, for example, what happened in your kitchen when you boil your soup or your water, it happens so rapid. Okay, that one takes millions of years for a whole cycle to go through. Okay, so it's super slow, but it's there. Okay, so this is basically in a nutshell what this chapter is about. So I don't know if there is anybody who came in late. We already have the question, okay, of the day. So again, seismic waves is when rock under the Earth's surface moves or breaks energy in the form of seismic waves, which causes the ground to shake and vibrate. Namely, it's an earthquake. Okay. Analysis of seismic waves provides geologists with detailed view of the Earth's interior. Because we learned from waves that waves actually have two key properties, okay? They have the property of being reflected and they have the property of being refracted. Based on the reflection and the refraction, I can deduce the density basically, because if I know where they refract, first of all, I know the boundary. Second, the level with which the wave changes speed then tells me the intensity of the density of the medium where the speed went lower or went higher. Okay, so that's basically, it goes lower, the speed is less for a less dense material. Like, for example, the speed of sound in the air is less than that of the speed of sound in water. Water is more dense than the air, of course. And the speed of sound on metal, for example, on the railroad tracks, it's faster than that of the air and faster than that of the liquid. So that gives me an understanding, because, of course, the density of the material, how dense it is, namely how elastic it is where the wave travels the fastest. So if the waves travel faster, that means it's denser. Okay. So that's why waves refract to begin with. That's why, for example, when we did the experiment for physics 11 between the air and, for example, a different medium like the water, in water the wave is the speed of light is slower, so the wave, instead of going straight line, is going to break. And the refraction now is a measure of basically how basically how fast light is traveling. I don't know, some of you are probably not sitting in physics 11. For physics 11, they were part of the lab is to calculate something called the index of refraction, and the index of refraction is the rate with which the speed actually is slashed for light. Okay, so the same thing is happening actually for seismic waves too. Okay, so here is the answer to the question of the day. We have the crust, which is about 10 kilometers, and for the that is for the oceans, of course. It's not that thick, and but it's a little bit denser than that of the oceans. That's why the oceans crust is actually sits higher than that of the ocean. This is due to the buoyancy. When we did the buoyancy, also, for example, when you take water versus oil is less dense or always floats upward. Think about it in that same way, that the continental basically crust itself is less dense than the density the oceanic crust, the crust under the oceans. That's why the ocean's level is below than that of, and because of both of them are sitting on some sort of a liquid in this case, namely the mantle. The mantle actually is divided into two regions into itself too. Okay, the lower mantle and the upper mantle. The upper mantle is the region that is molten, and the lower mantle is a little bit, because of the pressure, is not that molten, and actually it's solid. And again, all of these things we learn them from the seismic waves. Okay, the waves that occur in the because of the earthquakes. Okay. Then below that, of course, comes the mantle is the biggest chunk of the, as you can see, it's almost 2,900 kilometers. You remember the radius of the Earth is 6,370 kilometers. Okay. If almost 3,000 of that is just the mantle, then the other layers compose the other half, basically. So that's basically in a nutshell what it is. So basically almost half the Earth is the mantle. Okay. Then comes the core. The core again is divided into two regions. A big chunk of it, or the second big chunk of the Earth in terms of its structure, is that actually of the outer layer, core. I'm sorry. The outer core is a liquid structure, and we learned that from, again, the studies that have to do with the seismic waves. There are two kinds of seismic waves, two main ones at least. There is the P waves, which are compressional waves, and those compressional waves are just like the sound we do. Okay, just like when we talk about waves, these waves occur by compression and rarification, and they travel through the medium. They travel through all media. P waves, primary waves, they're called. They travel through all media. If you experience an earthquake, you actually see two distinct levels of earthquakes. I mean, at least there is the first wave that comes in, and that is the P waves, the primary waves. It travels faster than the secondary waves, or the so-called S waves. And S waves are actually transverse waves, okay, up and down. Well, transverse waves, they can happen, for example, in a medium that is thick, in a string, for example, they can happen in it, but they cannot happen in water. You cannot, for example, take water. It's going to break if you try to shift it upward and downward. Okay, there is no wave that's going to travel in it because it's loosely connected. So when you move one portion of it upward, the other portion will not follow with it. There is no basically, how should I put it? There is no it shears. It doesn't have the ability to. I'm looking for the word in here. There is no elasticity, vertical. There is elasticity in the bulk behavior. All materials exhibit that, but the liquids don't. So if there is an earthquake, for example, that happened in one side of the earth, of course, the waves will be bouncing off of the surfaces in here. So we can detect immediately the thickness of the layers. That's how we know they are. And they will bounce off of the other one, but immediately we distinguish that there is a difference in speed in here. We expect them to be moving with a certain speed, but if there is a difference in speed for the second wave that bounces off, then I know that the density of this material is not the same density of the other. So now I'm learning about density of this, the structure basically of what's going on in here. Okay, it turns out that this mantle is made mainly of basically iron and silicates. Okay. So that is basically the structure. Then I will have reflected both S waves and reflected both P waves, but there is no reflection in here coming from the after that for the S waves. I will have a P wave reflecting from this layer in here, or at least from below. So indicating that, hey, listen, in this case, I have actually, I'm sorry, there is probably transmission completely through the other side. The S waves will not be transmitted, but the P waves will. And I know the P waves will be transmitted because they can travel through a liquid. So I know that this layer actually is a liquid. Okay. And again, depending on how fast how much the speed in this case actually, because this is denser than the other medium, so the speed will pick up actually, it will be higher in this case. Based on that discrepancy in the speed, I can tell the density of this medium, and that's how we know it's made out of iron mainly, and with small traces of basically small amounts of nickel in it. So again, all of it has to do with the waves, has to do with the seismic waves. Okay, so that's how we know the structure of the Earth. Later studies actually revealed that the P waves, at least in some areas, because that's giving me again the structure of this internal structure, the core itself. What happened to them is they slow down. After they pick up speed, they slow down again. So that's why we know actually there is an inner core now that has a higher density than that of the outer core. So this is in a nutshell how we learn all of these things, which brings me to the second question of the day in here. The only way, or at least the only way so far that we know into how to study the structure of the planet Earth, at least, and probably for all of the other planets, is through seismic waves. Let me write it down for you guys in here. What tool? Scientists. See how it's all coming together now? We cannot learn anything about geology without learning about waves, okay, because they play a major role. They're the main tool, actually. We have seismographs everywhere that deliver seismograms all the time, and based on those studies, we're going to go and analyze them and find exactly what's going on in terms of what causes what, okay, based on the reflection and refraction. So it's based on waves, okay? And waves are actually rooted in classical mechanics, because that's basically where we learn about how things basically move in terms of the forces, the restoring forces, because you have an object that was at equilibrium, the Earth has no waves, is calm, and then now it's disturbed out of its equilibrium because of some sort of a stress that builds up over time. And we will find out exactly what causes these earthquakes to begin with. That is the buildup of the energy, again, that is due to the heat under the Earth that causes this whole crust to start to move, okay? And then when it moves, sometimes there is a resistance, and the buildup of that stress at some time there is a certain threshold with which actually there is motion. Now you have an earthquake that starts. So the Earth is at its equilibrium, just like the pendulum. You move it out of its equilibrium, you disturb it, Now it's going to oscillate, at least in that region. That oscillation propagates inside the Earth, and now you have a seismic wave. Again, in order to learn that, like the case in the pendulum, we have to use F equals to ma. So it goes all the way back to the second law of Newton. So the way to understand this is go back step by step into the process. So that's basically how this whole thing is built together. Okay, so what tool do scientists use to learn about the Earth's structure, and the answer, of course, they use waves or seismic waves. Okay, and there are two kinds of waves in this case, the primary waves and the secondary waves. Those are the two main ones. On the crust itself, there are two different kinds of waves too in that case. Okay, there is the we'll get them to the so-called love waves, and those are the waves basically that because the crust now can go up and down, or basically sideways like this one's in here, but at least that is the so-called love waves, as opposed to in the crust also it has also some compression waves. They are called Rayleigh waves. So, but those are not important. The main things are the S waves and the P waves. Okay. So this is again, this is the distinction between the primary waves and the secondary waves and the so-called waves, love waves and the Rayleigh waves, which are actually having this. The main ones, as I said before, are these two. Okay, this and this. Come on. Sorry, I'm not sitting on my desk normally where I have a better tool to draw stuff. Anyway, these are the two main waves, okay? And the primary waves occur first, and the secondary waves come second, okay? If you ever happen to be to witness an earthquake, and you happen to have your, I mean, at least part of your body, hopefully your feet standing on the floor that is leveled, you will feel the P waves first, and immediately you will know that few seconds later the S waves come. That's why animals sometimes they are warned. All of the basically the ground animals, rabbits and birds start to fly. They know that the S waves, the more damaging waves are coming, so they are warned. Okay. Based on the difference between the two, based on the time delay between these two primary wave and the second wave, we can find exactly where the earthquake happened. Okay. Of course. For a specific seismograph, it gives you a general idea where it's happening. For a secondary seismograph, it gives you more basically where the two converge is more or less where they happen. For a third one, now you know specifically, so you do triangulation in this case to find the epicenter of the earthquake. So the more seismographs detect the earthquake, the better you know exactly where it happened, okay, and how far it is and things like that, and then you can determine its intensity based on that, okay, how strong it is. We'll talk about that. So primary waves are longitudinal waves. They compress and expand the material through which they move. Compression and expansion occurs parallel to the wave's direction, okay, so they're waves traveling in this direction and they're going through that. Primary waves travel through any type of material, solid, rock, magma, namely molten basically liquids, water and air, so they travel everywhere. Primary waves are the fastest of all seismic waves. Okay. Then secondary waves are transverse waves. So we learned in when we did waves that there are two kinds. So there is a transverse. Transverse, they happen perpendicular to the direction of propagation. So the propagation is happening, for example, in this direction. The transverse are going up and down, or left and right, or they're going in some sort of a circular path, motion, like for example the Rayleigh waves. Okay, so secondary waves travel through solids. They are unable to move through liquids because they would tend to shear the liquid, and the liquid doesn't shear. I mean, when they try to move up, then the other part doesn't follow. So at that time they stop. Okay, so they cannot travel through liquids. Secondary waves are slower than the P waves. And they are the second to register, of course, in the seismograph. So you see a big peak, for example, for primary waves, and then another one that comes up for the secondary waves. Okay, and then you start measuring the difference between them and so on and so forth, and the intensity and how high they went and all of these things. So surface waves are the slowest waves. And the last to register on seismograph, Rayleigh waves have a rolling, basically, type of motion. They roll over in a tumbling, basically, fashion. Love waves have a similar to actually S waves, and they're actually going, horizontal, like a whip, basically, or you're trying to whip your eggs, okay? So the main waves, again, are the S and the P, okay? The P and the S, primary and secondary waves. So the most destructive earthquakes are caused by the passage of surface waves because they travel fast. No, that's not has to do with the speed. They occur in the crust, the densest layer. They all occur. They occur at the surface of the ground and shakes up and down and fro and from and to, so side to side. So basically, that's why they cause a lot of damage. Okay. Again, abrupt changes in seismic wave velocity reveal boundaries between different materials within the Earth. So, and the densities of the different layers can be estimated by studying the various seismic wave velocities. Again, the faster the wave is moving, the denser the medium is. So basically, the more elastic the medium is. The slower the wave is, the less dense the material, the medium is, basically. So that's in a nutshell how this thing is working, okay? It has to do, I know we didn't do the actual expression when we did that class, it has to do with the tension in the medium and also the inertia of the medium too when we did the waves. It's actually square root of T over rho has to do with the velocity itself, where T is the tension and rho is the density of the medium. So you can learn a lot just by looking at the wave speed, okay? You can tell the density, and once you know the density, you know roughly what materials makes it, okay? What is it made up of? Based on, is it closer to the density of iron, or is it closer to the density of silica? Silicate compounds, in this case, is close to 7.8, or is it close to lower than that? So depending on that, you can find exactly how the composition, okay? So Richard Oldham observed in the early 1900s that both the P and the S waves traveled the distance and then they encounter boundaries. And that is basically when we started to think of the different boundaries, and that's when he discovered the mantle, basically, okay? The S waves, they stop. They don't go any further than that, but the P waves continue, are refracted in that region, indicating that we're hit liquid at that point, okay? That's basically how we started to think about it at that time. Mr. Morovicic, okay, I think what is it? Not Serbian, the other country here, Croatia, okay, observed sharp increase in seismic velocity at the shallow layer within the Earth itself. So at that point, there was actually that's where the crust itself and the mantle is actually distinguished too. Okay, so that's how the crust-mantle boundary was discovered. Okay, so now this is basically the point I was trying to illustrate in here. Okay. Then further studies indicated that there was actually some sort of a shadow. When an earthquake, for example, if the epicenter happening here and you have several seismographs on the Earth, they detect these waves in here. They detect the wave as it's traveling through the mantle and comes back to the crust, and you can determine basically the different structures there. But there was a shadow in here, a region where actually the P wave basically seems to break in here into a different angle, indicating that it hit a different material with different speed. In other words, it was going in a solid, which was supposed to be fast, and then it slowed up, and then it picked up speed again. So indicating that we hit a different structure, different layer structure in here, and this region is a shadow between 105 and 140 degrees, and this is accurate. So from here, we started to find how thick the layer is. So if next time the Earth, there is another basically earthquake in here, then we can find that the shadow again between 105 and 140. Based on this information, we were able to determine the thickness of the mantle and the thickness also of this core layer where the liquid is forming. Okay. So further studies actually, and that was proposed by somebody else, actually I forgot her name, that the speed actually picks up a little in the middle, okay, indicating that going from a liquid to a solid again, and then slows down again, okay? So indicating that, again, we're going through this layer structure. So that's how we discovered the different layers of the Earth. We have solid, we have a molten rock, okay? And then we have a little bit denser material. Then we have completely liquid layer, and then inside of that liquid layer there is a solid again layer. And we can, based on the speeds, we can determine the densities. Based on the densities, we know the actual structure. This is mainly iron with traces of nickel. This is same composition. This is iron with silicate, and then the crust itself mainly is silicate and other composition, including iron, of course, and other metals that we discovered from previous chapter. Okay. So all of these people, okay, put together, they gave us a current composition: crust, mantle, and core. And the core actually made up of two different layers, inner and outer. Okay. It's all based on how the P wave is traveling. Obviously, the S waves just gave us the first layer, basically, up to, I mean, the first two layers, including the crust, if you want to, crust mantle, and then after that, there is no more traveling for the S wave. It doesn't go to the other side at all. It bounces back, and that's the end of it. So it's mainly iron, okay, and it's metals. Again, if you think about how the Earth was formed to begin with, it was from the debris that was in the area where the solar system was forming, and because of the heat, the heavy metals, basically in this case iron and nickel, the more dense materials, I should say, not heavy, started to coalesce inside, and the others start to move upward, and it's again because of the buoyancy, something that we learned again a long time ago. Okay. Namely, where the liquid now is displaced, and its mass or its weight must be equal to that of the material that displaced it. Okay. Inner and outer. The inner core is solid due to greater pressure. Again, the reason why it's solid is because the Earth itself, there's tremendous pressure on it, and at some point that pressure is not high enough, so that the actual composition is still the same, started to liquefy, and that's where we have the outer core that is actually a liquid. Okay. Again, further studies indicate that the mantle itself is actually divided into two different areas. There is the upper mantle, which is more plastic, has more plastic structure in it, basically structure that is a and then there is a lower mantle, which is actually denser because of the same reasons that the core, the inner core, actually is solid. Okay. And that is where a lot of heat is happening in here, and that is where the convection actually is happening, the one I was talking about earlier. Lithosphere, which is part of the upper, basically, mantle. I mean, that's basically where the crust is formed in here. That's basically, this one here talks about the rocks and how they're formed. Again, So this is just thickness, and again, the thickness has to do with the different breaks down in these waves. If you look back into the wave patterns, you see actually that they break a little bit differently at different regions, indicating that there is actually different difference in levels. Again, we talked about the fact that the density of the oceanic crust is actually denser than that of the continental crust, and the reason being is because of this. First of all, the mantle itself, at least below them, has high temperature, so that it's molten. So these things are floating again with it on it, and this is again has to do with the buoyancy. Okay, the oceanic crust is about 10 kilometers thick, and the continental crust is several kilometers. It goes from sometimes a little bit up to 60 kilometers. Okay, 60 kilometers in the context of 6,300 to 6,400 is nothing. Okay, so that's why the crust itself is super thin compared to everything else. It literally is like that of the egg in here. Again, this word isostasy has to do with how the two forces are balancing. In this case, the gravity and the buoyant force. There is an equilibrium that is reached, and that is where the layers are differentiated this way. Looking at the time, we still have time actually. We have a lot of people who didn't show up to class today. Again, this is the idea that was proposed in the early 1900s by Mr. Wagner. And when he looked at the Earth, basically the map, first of all, if you look at any map of the Earth itself and where the continents are represented, you can see that they fit like basically perfectly if you just move them backward. Now he explored the idea further by studying actually the rock formation, geology, basically fossils on the different continents, and also the other evidence in there, and all it points to the fact that his idea was correct. Okay, the biggest problem that he ran into, he called the entire continents when they were together as Pangea or universal land, and is what causes it, and he didn't know how to explain it. He proposed the idea of the moon, for example, probably has some effects on it, or whatever other forces that may be causing it. So his idea was dismissed until the 1950s and the 1960s, when the idea was revived, when we actually we were able to map the ocean basically floor and see actually that there is evidence for the continents being pushed against one another through the motion actually in there between, and there is actually the separation between the two plates actually in the at least in the Atlantic Ocean follows exactly the land lines and how the continents are actually separated. So that's what seems to be the push is, and that's how we know that actually his theory was correct, and it has to do with this basically convective motion convection that is going on inside the mantle itself, or at least the upper mantle itself. Again, so this is how they fit. Okay, North America fits with parts of Africa and parts of Europe, and again there was evidence for the fact that these two were connected this way. And then also South America and Africa were this way. Further studies actually indicate that there was actually, that this whole thing is actually where right now is the South Pole is, or at least the main part was where the South Pole is. Okay, South Africa, this portion of Africa, and this whole portion was where the South Pole is right now. So it was frozen ice. Okay, and this portion of the 500 million years ago or so was actually in where the middle of the earth, I forgot. The tropics are now. Okay, it was tropical region. So basically, and that's not only it moved apart, but it moved actually northward. So that's how we learn about it. So again, a lot of evidence for this continental drift in the beginning, but the biggest block or the biggest problem that he ran into is to explain what causes it. So Mr. Wagner could not explain how continents moved. Without his idea was dismissed. Okay. So So the mapping of the seafloor, basically, we found the huge mountain ranges and also trenches, okay? And they follow actually the same continental path as the continents outside on the top they look like, okay? And this is the explanation now for the force edit, okay? You have this convection in the mantle itself, and this convection is pushing basically material into the seafloor and pushing the two plates against one another. And where actually the continents themselves, the continents with the ocean they meet, basically the two crusts where they meet, actually there is actually a motion, because now again we're talking in terms of density again, in terms of buoyancy, because the continental the oceanic plate is denser, so it's going to go below that of the ocean, and this motion is called the subduction, okay? Because the upper plates of the continent is pushed upward, and that of the oceanic crust is pushed downward because again of the density. Okay, so again that's how this force is moving them. So we know that it's correct now. Okay. And there's also another study that has to do also with the magnetism. So if we take rocks from different places on the Earth, we will find that the magnetization indicates that it has changed over time. So, and because the magnetic poles, because the Earth apparently, because the molten rock inside the core itself is sometimes actually slows down and reverse motion. So the polarity of the Earth is changing. Actually, it's not fixed. Now, based on the rocks that we see, they give you actually a date into when they were. Looking just at the magnetization orientation of the magnetic field in them, you can tell the history of when they moved last. So there is more evidence to the continental drift than just one thing. It's not just like taking the two continents, putting them together, or all the continents and putting them together. So again, the spreading of the seafloor is due to this upward motion from underneath because of this convection. Okay, and that's how they spread, and they push against the continental crust. So the plate tectonics is really a theory that explains all of this phenomenon together. So again, that's how they're structured. There is more evidence to that and more descriptions in here. I would recommend that you guys go through the chapter itself, because I'm feeling kind of we don't have a lot of audience today. This is kind of disappointing a little bit. It feels like a holiday, doesn't it? For the few who are here. I'm not getting any feedback from you either. Or you're sleeping, just like me. Okay. Okay, so we'll make it fast in here. Okay, so we still have a couple of items to touch base with. Okay. So again, I talked about the subduction and how layers they push against one another, and it's an important concept because there are different kind of ways they push. First of all, you have the diverging plates, where two plates are pushing against one another, like what's happening, for example, inside the oceans, in the middle of the oceans. So this is a diverging. So they are trying to basically, and that's how. I'm sorry, the plates themselves are diverging. They're moving away, again, from what's happening in the middle of the oceans. And also you have the convergence of converging of plates. Basically, this is basically where the two plates are meeting one another. When they meet in this point, what happened, again, I talked about the fact that the denser one will go below the less dense one. And this is like what's happening, for example, in the Pacific Ocean near the, I think near the Philippines, where the area there can go all the way to 11 kilometers for the seafloor, for the oceans in there. 11 kilometers is a lot of depth in the water in there. It's much deeper than the highest mountain in the Himalayas, which is what, like 8 kilometers or so. Okay, So if you take the entire Himalayas and put them in that region of the ocean, they will completely submerge, and you will have some water left. Okay. And then you have a different kind of basically where they actually slide against one another, okay? Where they form faults, okay? So they don't necessarily have to basically push in or push out. They can actually slide against one another. The converging plates, okay, so this is basically for the where they're this is the diverging plates in here. So for the divergence, so again the plates are moving apart from one another, and the material is always coming out from the mantle itself to the to fill the gap and form a new part of the new plate. Again, this is a subduction I was talking about in here. So this is the convergence when they are coming together, and the denser one, usually the oceanic plate, will go below that of the continental plate, or crust, I should say. Okay, because of this motion, what happened in here, the magma is pushed upward, and when the magma pushed upward is going to come out either in the oceans or is going to form basically volcanic islands like the Hawaiian Islands. Okay, or actually inside the continent itself is going to create this volcanoes. Or for mountains, like for example, how India is pushing against Asia. That's actually where the Himalayas mountains are being formed and actually continue to be formed, because these two are still pushing against one another. This is the example I was talking about, the Himalayas mountains. And this is the shearing I was talking about in here earlier. That's another phenomenon also when the two plates are moving against one another. Like for example, how California is basically, or at least the San Andreas fault, how it's formed actually, how it's because of the motion of this part rubbing against the motion of the other part. And at some point, Los Angeles in the future, millions of years from today, will be shifted to some northward, okay, whereas the other plate is coming downward. Again, the compressional stress, so those are the ones that form different kind of, or at least the evidence for this plate tectonics is different kind of stresses, basically when two objects are stressing against one another. This is stress that can build up over time when two plates are pressing against one another, or there is a tension, basically, which is the opposite of the stress, or the shearing, basically, that where one slides against the other. Of course, this builds up of pressure over time will just basically build up our pressure until at some point it's going to give way, and that basically shows itself in some sort of an earthquake, okay? Or it forms at least faults, okay? Or deformations in here in the mantle itself. So this is how the faults would work would basically form in this case because of the motion of the different plates in here. One slides against the other, and now fault forms like the San Andreas fault. Okay, we have a few slides to go through. Again, earthquakes are, this is the shearing that I was talking about. And it always happens usually where plates meet, okay, or at least crust meet. For example, in this case, the oceanic plates, and they are different actually plates in this case, they're moving against one another or compressing against one another, or basically pushing against one another, or between where the actual oceanic basically crust and that of the continental crust also meet. Okay, again, this is the fault lines basically where the earthquakes, and more or less also where they happen on Earth. Okay, again, there is a little separation between Africa and Europe and here, and all of these places is where most of the earthquakes happen in here in Iran and the Caspian Sea and the Black Sea also, where there's a lot of earthquakes also happen because of the same phenomenon. That again, earthquakes are they can occur between plates, and also where there is the deformations, and they form faults, and those faults, that's where the pressure builds up, or the stress builds up, and over time that's when the pressure is relieved. Again, as earthquakes are measured in at least the Richter scale. That's basically how we started with it. Okay. And the Richter scale, or Richter scale, is actually a logarithmic scale. Okay. Let me stop sharing the screen quickly here to talk about this point. So logarithmic scale, to give you an idea of what it is basically, if you took the math class, you're fine. If not, this is basically in a nutshell what it is. So for example, if I have something, okay, this is an earthquake of level 1, and this is an earthquake of level 10, okay, on the Richter scale. This, between 1 and 10, it's not just 10 volts. That's not correct. It's actually 10 billion times stronger. Okay. The reason being is because this is a logarithmic scale. This is not a linear scale. Okay. Actually, let me explain a little bit of what the log is. And it's on a base 10, okay? So because the log depends on the base. So the base 10 is how much power you're raising to what number. 10 to the power 1 is 10, okay? So this will be on the Richter scale 1, okay? 10 to the power 2 is 10 times 10 times 2 times. 10 to the power 2 is 100 actually. Obviously, this is recorded on Richter scale as 2, the power only. 10 to the power 6, for example, just reads a 6 on the Richter scale, okay? But actually, this is a million, because 10 times 10 times 10 times 10 times 10, 6 times is 1 million. Okay. Again, when people were looking at this, they were looking at it in terms of basically the intensity on the seismograph. Okay. So if this is this much and the other one is this much, this went from a level 1 to a level 2. This is this much. So if I have a meter scale in here, so this is 1 centimeter, and this much is 1 meter. So in this case, I went by a factor of 100. Okay. So I went only by 2 degrees in this case, okay? So going with 1 centimeter into 1 meter, it has to actually span my entire screen in here to really give you what 1 meter would look like. This is factor of 2, okay? Not 100, a factor of 2. So if I go kilometer, which is from one to the other side of basically of the street to basically where the next store is, you have to, it's a little bit of 2/3 of a mile. So that is, I went by a factor of 3, okay, on the Richter scale. If I go 10 kilometers, which is 6 miles, I went only by a factor of 4, okay, by a factor of 4, compared to this unit, okay, compared to just walking from here to here. So I only went 4 times more on the Richter scale. Of course, you're telling me, oh, what do you mean? It's 6 miles. You cannot walk 6 miles. It's going to take you about probably 6 hours or 7 hours to walk, I mean, a normal speed. Yes, that is a factor of 4 on the Richter scale. If I go 100 kilometers, which is 60 miles, I went only by a factor of 5 on the Richter scale, just to give you an idea, okay? If I went to 1,000 kilometers from here to Dallas, basically, I went by a factor of 6 on the Richter scale, on my units in here, by a factor of 6. See how big it is? If I went from here to 10,000 kilometers, basically, from here to, I don't know, probably where Madrid is in Spain, okay? Then I went by a factor of 7, okay? if I go to 1 million kilometers, 1 million kilometers will put me way outside of the Earth. We are very much way outside of the Earth, okay? And actually we have traveled, so, no, I'm sorry, 100,000 first, I missed 100,000. 100,000 is almost 2/3 of the distance from here to the moon, okay? Which is very far also away. It's outside of the Earth. That means I'm a factor of 8. 1 million kilometer would put the moon way back, okay? 3 times further than where the moon is. I'm a factor of 9. 100 million kilometers is basically what we're talking about in here. And that would put me outside of basically the sun, or at least very close from the sun. Okay, 100 million kilometers is very close from the sun. I was way past Venus, and I'm very close from the sun if I went to the direction of the sun. Or I'm very close from, or at least spent a big distance from here to where Mars is. To get into the factor of 10 compared to this distance. Okay, so this is just to give you an idea that this is sometimes misleading. You think, okay, an earthquake of 2 and an earthquake of 3 is not as bad as 2. Well, it's 10 times stronger. Okay, just to put things in perspective. Okay, earthquake of 2.4 and an earthquake of 2.5, they are not slightly different. There is a big difference between them because of this this logarithmic scale. Okay. I just wanted to bring this point because sometimes it's kind of, again, when things, why is this screen is black? So just to give you an idea of the scale in here, you really have to have an idea about it because sometimes earthquakes are reported and you really have to have some sort of a notion of what they mean, okay? Okay. The tsunami is actually, that's a sequence, that's actually a result of what earthquakes do. Earthquakes, when they happen again, they cause motion in the liquids. In this case, in the liquids, the amplitude is so big, but because the ocean is so deep that there is only a slight motion upward. So if you happen to be in the ocean in your boat, you're not going to feel the tsunami passing by. Or again, we call very slow motion upward and downward. But as it comes to the closer from the beach or the seashore, I mean close to the ground, then that amplitude is amplified and is going to suck all of that water, just make up that amplitude that is traveling. And tsunamis are the so-called solitary waves. Basically, they travel in one direction, and then after that they dispose a lot of liquid where they go. Okay, they were usually followed by waves, but those are secondary waves. They have nothing to do with the tsunami. So this is in a nutshell what this chapter is all about. There were 2 questions in it, so hopefully you guys will catch them for those who did not attend the class. And I really don't want to repeat them because I don't want people to skip toward the end to know exactly what the questions are. So I want them to go through that so that they can catch the questions. Okay, I'm going to stop the recording now.